Our first proof is done by using polar coordinates, which solves for the integral using multivariable calculus. Probably the most widely known proof. To begin with, we take the base integral and square it, and this lets us further transform the integral later. Next we expand the brackets, and as of right now, both integrals are with respect to x. However, something to consider is that often the variable name within a definite integral is largely irrelevant, since by the end we solve for some real number and not a collection of variables. So with this in mind, we're going to keep the first integral with respect to x, but the second with respect to y. The integral can be written as a product of these two, and by using exponential laws we can claim the exponent further. And now we're left with the double integral with respect to x and y, leaving us a multivariable calculus problem. Trying to solve for this within the Cartesian plane is hard, essentially leaving us no better off than we were to begin with. However, by changing the coordinate system, this integral, which would otherwise be difficult to solve, is now much easier to compute. We can immediately convert the exponent by knowing that x squared plus y squared equals r squared. Next we take dx dy to be the area Cartesian and convert it to be r d theta, which is the standard measure of the plane and polar coordinates. Finally, for the limits, we can see that in Cartesian, the limits represent all the values of x and y. So similarly in polar, we'd like the limit to reflect the entire plane again. So for our limit, we're left with 0 to 2 pi and 0 to infinity. Integrated in the integral, we can get minus 1/2 times e to the minus r squared, integrated between the bounds of 0 and infinity. Expanding this, e to the minus infinity becomes 0, and e to the 0 is obviously 1. So this leaves us with minus half, which then becomes a half. Half theta from 0 to 2 pi becomes half times 2 pi, which leaves us with pi. Finally, applying the root, we finalize a proof to give us the Gaussian integral.
So this is a geometric proof of Gaussian integration. It uses single variable calculus to find the volume of the Gaussian function, which helps to find the integrated Gaussian. So I've mocked up some Gaussian functions on the 3D plane in Python, which are going to be very useful to explain this method. So the first way to find the volume is by taking horizontal slices of this shape to form disks. We can then find the area of these infinitely thin disks. So as seen here, there'll be a disc, and they're all infinitely thin. We can then find the area of each of these disks, sum them up and find the whole volume. So the area of one disk will be pi r squared, since they're circles, and in this case the radius is just y. So the area of one disk can be given by AZ, and it's pi y squared. We can get AZ in terms of Z by finding Y in terms of Z, and we do this by setting X equal to 0. We can then solve for Y by taking ln of both sides, and then Y squared is simply equal to negative ln Z, and we can sub this back into the area of the disk function. Then we simply need to integrate this area between 0 and 1, since that's the height of the Gaussian. Start at 0 up to 1. Then we're given the volume here, which is negative pi times this, which is negative 1. And we end up with the volume as pi. So the next method to find the volume of the Gaussian is using vertical slices instead of horizontal slices. So instead of getting these disc shapes here, we vertically slice it, and we end up with shapes like this running along these lines all the way up that are infinitely thin. And again, we're going to sum up their surface area to get the volume of the whole thing. So these go off from negative infinity to infinity. So the equation here is each one of the surface areas of these vertical slices is given by the integration between negative infinity and infinity of e to the negative x squared plus y squared. Since we're integrating in terms of x, we can take out the e to the negative y squared term due to integer laws, and we actually end up with this term here, which is the Gaussian integral, which we're going to represent by I. So the surface area of each of the vertical slices ends up being e to the negative y squared times the Gaussian integral represented by I. Then we can go further down and sub this surface area equation into our volume equation. Again, integrating between negative infinity and infinity, and there it is again, the Gaussian integral, this time in terms of y. we can go ahead again and sub in I, and the volume becomes I squared. Now this is the clever part, where we equate the two volumes, since they're taking the volume of the same object. So the volume in the first method was pi, and the volume in the second method was I squared. So it becomes I squared equals pi, and then we can rearrange as I equals the square root of pi. So the Gaussian integral is equal to the square root of pi.
Hi, I'm Thomas Tra, and this is part 2 of the team assignment where I'll be covering another Gaussian integral proof, namely, proof via change of variables using substitution. This time, we let j be the integral from 0 to infinity of e of negative x squared dx. Since x is used as a dummy variable, we can also let the function be equal to the same integral, only replacing x with y. Now similarly with the previous proof, it can be written as j squared, which allows us to apply some substitutions later on, which when simplified gets us a double integral from 0 to infinity of e of minus x squared minus y squared dx in brackets dy. Now in the previous proof we used multivariable calculus using polar coordinates in order to simplify the integral. This method differs a bit in that we need to establish 3 steps of substitution before continuing. First, let's set x equals yt in the inner integral, where y is fixed. We get this by equating t equals x over y, which becomes x equals yt when bringing over the y. In the same fashion, let's set dx equals y dt. And finally, 0 equals yt where t equals 0, and infinity equals yt where t equals infinity. Now let's substitute these steps into the integral, which becomes this, replacing dx with y dt and x with yt, which can be simplified down even further to become this, moving the y over and switching dy and dt. This interchange of integrals is justified by Fubini's theorem for improper Riemann integrals. Even though e of minus y squared doesn't have an antiderivative, this function does, and simply just becomes a constant. From here, we can integrate as such. From 0 to infinity, and subbing in infinity and 0, which becomes the integral from 0 to infinity 1 over 2 multiplied by t squared plus 1 dt. And from here we can apply this arctan rule to integrate as such, which becomes half tan inverse t from 0 to infinity. And from here we just substitute infinity, which can be done by substituting a very large number, which becomes pi on 2, and 0, which becomes 0, and altogether j squared equals pi on 4, and from there we bring the squared over, square root this, which becomes j equals square root of pi on 2. And that concludes my proof.
This proof uses differentiation and only single variable calculus, not multivariable calculus, to calculate j. Let j equals the integral. We're trying to differentiate j, and as this is an improper integral, for t is greater than 0 we set at equals this integral with a infinity equals j squared. Now we differentiate this with respect to t using the fundamental theorem of calculus and get. From here, we want to change upper limit of the integral t into something else. We can use substitution let y equals xt. This will give us x equals ty. If x equals 0, then ty would equal 0 and y would equal 0 as well, as we know t is a big number and one of them has to be 0. If x equals t, then ty would equals t and y would equal 1 for the same reason. So we get this. At this point, we have to find its antiderivative, so we can change integral to make it with respect to t, as find the antiderivative with respect to t would be easier than find the antiderivative with respect to y. Taking dt out of the integral, we would get. We can call this integral bt. From this, we know that a prime t equals negative b prime t. If this is true, then we also know that at equals negative bt plus c is true to anti-differentiation. So, now we can input a value into t before integrating. An easy value we can use is 0, because an integral from 0 to 0 just equals 0. By putting in t equals 0, we remove left hand side and get. Integrating this, we get negative 4 plus c, and c equals 4. And putting this back in the original equation, we get. In this last equation, if we let t equals infinity, then we'll get j squared equals 4. Therefore, j equals 2.